prepared ourselves for controller designs. And the first one is I want to give you is a general ideas. Okay, so from this section, basically, I want to help to classify what is the transient response and what is the steady state response. Okay, and here I'm going to use the example to demonstrate the concept. Basically, the idea is this. Before we go to the solve in detail, the idea is this. This is the dynamic system. And this dynamic system basically will take up basic two pieces of information to drive his dynamic response. And the first information is we take the initial conditions. Okay, and the second one is the system is to take up any external loadings. So that is the so basically that is our input. So by taking the initial conditions, basically initial conditions will contribute after the dynamic system to respond to the initial conditions will contribute to the transient response. And on the other side, due to the input, what we call the command, and this one will actually respond to steady state. Okay, so that's the concept. And in our studies, we have learned the transfer function. Transfer function is the output response in a ratio to the input in the S domain. And when we study the transfer functions, we ignore the initial conditions. So that is the fundamental assumptions for transfer functions. So basically, in your learning of the transfer functions, actually the transfer function taking care of is this part only. Okay, so hopefully with this kind of the pictures can mentally build up something for yourself. So we can consider one example here, and to demonstrate this concept. So we consider two second order systems. Okay, so and this is the initial conditions x 0 equal to 1 and x. Okay, so those are the initial conditions, and this is our loading, or we call the input, and xt is the response, and we call the output in terms of the control terminologies. Okay, so now we want to solve for the response of the system. Basically, we're going to solve for xt. And solving for this equation, there's a couple ways you can try, and you can use homework 1, and we take in Laplace transform, and then we take the inverse Laplace transform, and we can find it. And traditionally, and we can try the traditional the solution process when you solve the differential equations. Okay, here I try that way. So for example, for the transient solutions, so basically xt is equal to x and transient solution part, and plus the x steady solution part. Okay, so here let me split into two portions. So for xt is a transient, or we call the homogeneous solutions. Okay, and this one steady state is called a non-homogeneous solution. That is the terminologies we use in differential equations. So for the homogeneous solutions, by this, we first solve for the characteristic equations. And for that case, s squared plus 2s plus 5 equal to 0. So s is equal to minus 1 plus 2z. Okay, and that is a root. So therefore, xt will be equal to, per the characteristic root we have is exponent minus t and times a cosine 2t plus b sine 2t. Okay, so hopefully you remember the way we did it, but anyhow. And x is obtained by, this is the non-homogeneous solutions, and non-homogeneous solutions is this. In the differential equations, we simply look at the non-homogeneous term, which here is the sinusoidal functions. So in here we assume per the standard procedures, and we assume this should be sinusoidal functions in terms of combination sine and cosine both, and must be in the same pattern t. And here I use alpha and times beta. Okay, so from here we have other forms. So therefore, we have the combination of the homogeneous term and non-homogeneous term. Here in total we have 4 parameters, a, b, and alpha, beta. 4 parameters we can solve for. Okay, so this is a very traditional solution process solving differential equations from DFEQ. So by doing this, and we can try is we try to solve for this one beta. We can try to solve for this one first, and so we introduce x, and x dot we take derivative, and we take the double derivative. Okay, so basically this one, let me say this is alpha sine. Okay, let me write it again. And this one we take the derivative, basically that is alpha cosine t minus beta sine t, and then double derivative is minus alpha sine t and minus beta cosine t. We introduce the 3 terms into our differential equations, then we can solve for alpha and beta. Okay, so the coefficients, introduce the 3 terms into equation 1 here. So then we can compare coefficients of sine t term and coefficients of cosine t term. Okay, so the coefficients of sine t, and that one basically is on the left hand side is minus beta 2 beta plus 5 alpha. Okay, and the coefficient of the sine t on the right hand side equal to 2. Okay, the coefficient of the cosine is minus beta plus 2 alpha plus 5 beta. And the coefficients of the cosine term on the right hand side equal to 0. So from here we can solve for alpha and beta. So therefore alpha equal to 2 over 5 and beta equal to minus 1 over 5. Okay, so with these things, then we can have the expressions of xt. Therefore xt will be equal to, we put everything together, minus t and a cosine 2t plus b sine 2t, and plus the particular solutions, and which is this one. So let me write it out, and that is 5 over 2 sine t, and minus 1, 5 cosine t. Okay, so this is the complete solution to this one. To solve for A and B, we can use the initial conditions here. Okay, so apply initial conditions to solve for A and B. Okay, so here you simply plug in the initial conditions. That is, this is x0 and this is the x dot 0. Okay, so plugging those information should be very easy. So therefore, we can have the A equal to 6 over 5 and B equal to 2 over 5. Okay, so with those things, then we can plug in. So to save my time in writing, so let me here directly introduce A equal to 6 over 5 here, and B here is 2 over 5. Okay, so that is the total solutions, and this is a complete description of the system response. So the total system response equal to transient response plus the steady state response. And this one is the total system response. It's this one. Okay. So now we mathematically we obtain the response here, and now we can try to plot we can analyze the system response. And how can we say the system response is transient or steady state? The steady state, by definition, is when time go to infinity, the form of the response of the solution when time goes to infinity, and that is called the steady state response. So here we can plug in, say t equal to infinity, we say what happens. That means this term will approaching to 0. Right? Because this is exponential decay. Okay. So basically this term is what we mentioned as the transient response, because that's going to decay to 0. And this one you can see in our solution process, this term, if particular coefficient A, B are involved with the initial conditions. So initial conditions very clearly contribute to the transient response in this example here. And the remaining, when time goes by to infinity, the two terms will keep oscillating in terms of the frequency, in particular in the frequency of 1. And that is to follow the given loading. So the steady state response is simply determined by the external loading. Eventually the system is going to follow up the same patterns of the external loadings. Okay, so this is the part here. Okay. And so keep those things in mind, and in controls, and again in the transfer functions, this is the portions kind of more or less, and this is the transfer functions. And let me call this is y of s, and this one is called the r of s. So here the transfer function is y of s and divided by r of s. So which means if you want to determine the transfer functions, you simply exclude the influence of the initial conditions. So that means here you just ignore that one, these portions in your Laplace transform. Okay. So with this kind of mental pictures in mind, then we can begin to have the gradually get into the time response of the different systems. So this is the dynamic system. Then go to the next sections, and we can start from the simple system, and that is for the first order systems. And again, these chapters we're going to focus on totally in the time domain, try to get more understanding of these systems. Okay, first order systems, and here the typical example, the first order system have this kind of characteristic. So for example, the output to input in the transfer functions, okay, and that one, something like this. In the denominator, the highest degree is only 1, okay, and from there we can convert it into the time domain. And typical transfer function is something like this. And so TS, so say here we only concerned about the steady state response here. Okay, so these are transfer functions. So this one, this is a block diagram, we can convert into that. And so therefore, the time response of RT, the YT. So YT is the output. Basically here is this. You can see the YS from here, because the YS equal to 1 ES plus 1 times R. Okay, so here the YT simply is the inverse of Laplace transform of that one. So inverse Laplace transform of Y. And what is Y? And Y equal to 1 TS plus 1 times RS. Okay. So the response of the output, and by ignoring the initial conditions, this is the one here. So now depends on the kind of the loading, the input here, we could have a different output response. So I will talk about is few scenarios. So I'm going to talk about is 3 scenarios. So that could have for this R here, we could have the 3 options, and one is we call the unit impulse, and we could have is the unit step, and we could have is the unit ramp, and etc. Okay, and the 3 are the most common things we can see. So from here, the first one is we call the unit impulse response. Okay, and the unit impulse response of the first order systems. So from here, the unit impulse response, that means RT and equal to delta T. And so that means the RS equal to 1. Okay, so when RS equal to 1, therefore YT equal to Laplace inverse, then we plug in RS equal to T that there. So this one multiplied with 1 here, right? So this one, actually we have described this one in our previous lectures in the last couple weeks. So this one should be very straightforward. So we do this one. So that right now we do this. And again, from our Laplace transform tables, we have is S plus A, and Laplace transform is E minus AT. Okay, so here we can try to convert that one. So E convert into that one. So here is S plus T over 1, and then this is right. Good. Okay, I simply try to convert into this form. So we have this one. So that one will be equal to T, and this term will be equal to E minus this one. Okay. So now for this case, we can look at the systems. So this system is something like this. So I'm going to draw the response of the system. So this system basically is in exponential decay, so very straightforward. Okay, the initial value, the starting value is 1 over t here. Okay. And this is that's it. For the second case, unit step unit step response. Unit step response is when input equal to 1. So that means if we draw at time, this is our input here, RT, and that value equal to 1. Yeah, that's called the input, unit step input. So in this case, we have the R of S, this one equal to 1 over S, right? Okay, so therefore we calculate YT equal to Laplace inverse and TS plus 1 times. Again, right now we introduce RS here equal to 1 over S. I believe everyone should be able to do it, right? So that should be, so now we can do this one. So that one here, we factorize. This one basically we can factorize into two terms, SA plus TS plus 1B. We factorize into two terms, and then we find the coefficient of each terms, right? Okay, so now for this case, allow me to do it quickly. And here the A equal to 1, and this is minus 2. Okay, so after the factorizations and do the simple calculation, we can find those things, and then we can proceed. So now basically here individually, Laplace inverse of 1 over S plus Laplace inverse of minus T, Ts plus 1. Okay, individually do it. So the first term equal to 1, and the second term equal to minus, and that one basically follow up the previous calculation is the minus the E over T. Okay. Can you follow me? This one should be okay, right? We know the Laplace transform 1 corresponding is 1 over 1. So for this one, Ts plus 1, because this one is again equal to 1 S plus 1 over T, okay? And with this one, we know the S plus A corresponding is E minus AT. So with this one, you can compare to this form, basically, yes.
Right there where your finger's at. No. Yep. The lowercase and capital T are backwards.
Oh, yeah, sorry. Good, thank you. Okay, now for this one, we can draw the response. So y. So from here again, it's exponential decaying, and decaying is we can draw a few dots and we tracing the dots. Okay, that's the quickest way. And actually, if you do it that quickly, then that is something like this. Okay. And I directly show the result, but quickly you can do it is you can simply list a few points and you trace it, you can get it. Okay, so that's the result. You can see basically for here, you can see eventually YT approaching to 1. So that means when time go to infinity, the Y value equal to 1, because this one will become 0. So this one, that's saying, when we said the response of the system go to infinity, that means the steady state the steady state response equal to 1. Okay. Steady state response equal to 1, and our input equal to 1, so that means eventually the system will follow up to the command, will follow the command exactly without any error. Okay, so that is the feature of the first order system. And then as far as the from the beginning to certain finite time, then here you can see that is called the transient response. The transient response is all the system has its kind of initial term there. So you need to respond and give the system time to go respond to the certain level. So that for this response of the first order system, we see there's no oscillations. Simply it's gradually climbing up to the designated value here. And here for the transient response, we have certain features. In particular, here I want to give you the time. So for example, when t equal to t, capital T here, okay, and then for this case, we can calculate the value of the response, and corresponding to here, we do the calculation. We simply plug in t equal to here, so basically this value is equal to 1 minus e minus 1, and this value actually is equal to 0.68 or 67 something, 6328, okay? So this one, this is the very special value here. When here I want to introduce one term is we call the time constant. The time constant basically is when the system responds reaching to 63.2% of its designated value. Then we define the time corresponding to that one is called the time constant of the system. So this one is called the time constant. Simply time constant just tell you how quick a system can respond. And simply it's kind of the measurement and kind of index to which the transient response. So if for example, if the system have a time constant say 0.1 second, compared to the other the slower system which has a time constant say 1 second, then from here you can see the system which one is quicker, because it take a little bit. It takes 0.1 second to reach about 63% of the command value. Okay, so usually from the time constant, designers or engineers can tell how quick the system will respond, how quick the system is, and that will give the grab certain feelings. And for most of the electronic systems, if you design the RC circuit, the resistors and capacitors, they will come up with the one or the first order system. And those kind of the electronics, they have a time constant, usually is measured in microseconds or less. Okay, so if you remember any, or you even have taken instrumentations, immediately from oscilloscope, you can see. Then using the wave function, if you're going to use the function generators to see something, then probably in that function generators, you must come up with appropriate function design with appropriate frequency, and that frequency must match with the time constant. Otherwise, you won't see nothing. Okay, either the function could be too fast, the system cannot catch up, or the function is too slow, the system basically responds as a constant. Okay, so this is the very important the physical the terms here. Okay. And the third one, unit ramp response. When the unit ramp response is this one is simply equal to t. Okay, that means simply it's the time. This is our input, and simply is taking the slope equal to 1. Okay, that's for the unit ramp. So basically, this is the time constant rate control. Constant rate control, basically the input kind of increasing. So for this case, this is 1 over s squared. Okay. So now we see how can we calculate yt. equal to Laplace inverse of 1 ts plus 1 times s squared. Okay, so here we introduce rs equal to 1 over s squared to there. Then we do the calculations. So here we can convert it into a few things. So from here, you can see basically that is a term s squared times ts plus 1. So you have to factorize into how many terms? You have to complete the factorization. So s squared plus ts. Okay, so T is ABC. Okay, and do it, finding the coefficients of ABC appropriately. Okay, and sometimes some trick is this. Students before they say, oh, that is the two terms, then my factorization is this. Of course not. It's not complete. Okay, so you have to add in this term as well. Okay. So now that result will become 1 over s squared minus t over s plus t squared and ts plus 1. Okay, so after finding the ABC, we have those things, and I copy from my solution here. So there we individually taking the inverse of Laplace transform on the individual terms. So on the individual terms, we know, say, 1 corresponding is 1s, and 1 over s squared is corresponding to t. So we copy from here, this first term is t. The second term is 1 times coefficient t. So this is 1 here. Okay. The third one, simply, again, like follow up our the previous example here, and so for that example, if this is t squared, then that is t. Okay, so that corresponding is t times exponent t over t here. Okay. So now for this case, and again, before we drawing the curve, we see what happens. So when t go to infinity, we try to study the steady state value here. And when you write the steady state symbols, and you don't need to, because this is steady state value, you don't need to write of time, because time is not a parameter, not a variable anymore. Okay, so so here is basically we're looking for t go to infinity, the value of t. Okay, so in this way, you can see this one, basically, t is go to infinity, right? So, and so let me say t equal to rt. How about that one? Okay. Basically, this one is our input, so let me replace that one with this one, okay? And minus t, this term becomes 0, so we don't need to write it. Okay, so this is the steady state value. Compared to our input, of course, go to infinity will become infinite. But you can see the difference between the steady state response to the input. They always have this discrepancy of constant value. So when we draw it, t, and let me use this one as my input. So this is my RT. And the output, I'm going to draw this one. Basically, the output is 4 behind. The value is less is less than RT by that much. So this is my output here. So at this time moment, let me trace a few lines here. Okay, let me go a few lines here. Okay, so I don't care. Right now, I don't care about the transient first. So at this moment, eventually, that is the value here, and that is the t. 4 behind, this is t. So basically, eventually, the response is something like this. Okay, so that is steady state. And as far as the transient, so transient is closing, is the time when closing to 0. Then you can add in using the whole equations, and you can plot a few points and trace the point. So basically, the transient response will be something like this. Okay, so basically here that's a little bit exponentially rising and to the certain value here. You good? Okay, if we want to be very precise, then we can put a very precise point here, but here I just schematically draw this one. So again, this value equal to t, then this is our output yt. Yt fall behind the input by a constant amount, and that is determined by this one. Okay? Any questions? It should be very easy. So, for example, in the test, I ask you, say I give you a transfer functions and ask you to calculate the unit impulse response. Then can you do it? You can do it. You simply go to the section 1 there, and with input r of s equal to 1 and do the calculations. Okay. And now I'm going to use the different colors and to indicate if you're going to use MATLAB to help you to verify the result, and how can we use MATLAB program to do this one. And so, for example, here, let me make one example here. Okay, so. So from here, for unit step response of yt, in MATLAB you can do this one. The first one, you from here you can see the y will be equal to 2s plus 1 times rs, and when we deal with the unit step input, so basically rs equal to 1, right? 1 over s, sorry. So that way basically is become 2s squared plus s plus 0, 1. So when you do the unit step response, then you can do is these numerators equal to 1 and denominator equal to 2, 1, 0. And then you're going to use this command for the step numerators and denominators. So after you hit returns, then MATLAB will give you something, also will give you a certain curve similar to this. Okay. And for the unit run, then we can see how can we do it. So for example, again, using the same example here, so y over r equal to 2s plus 1. Okay, so y equal to 2s plus 1 times r over s. So now for this example, s equal to 1 over square. So 2s plus 1 times s squared. Okay. So how can we do using MATLAB? I'm going to still using MATLAB and step input. I'm going to still using this command. Okay, kind of the, and see how can we treat the, how can we treat information to this. So by doing this one, I want to rearrange such that I made a mistake. Okay, and I need to correct my mistake using the red color. Okay, so for the unit step input, I think the most we stop here. And this is a step input. Basically, this is the Laplace transform of the unit step input. So the numerator, denominator is only this portion here. Okay, so here is 1. So here I need to modify this is 2, 1. we only input the systems that is for this term that multiply with 1 over s. We only input this system. You good? Sorry, that's my mistake, and I didn't use for haven't used for a long time. Look at my notes. So now for this one again, we need to convert the system into the same template. So the template we can try is this. So basically this one will be equal to, that one will be equivalent to something times 1 over s. So that will be equal to 2s3 plus s squared and 1 here. Okay, so now for this case, the numerator will be focusing on this system. The system multiplied with unit step response. So here the numerators equal to 1, and denominators equal to 2. We write the coefficients from the decreasing orders, and it's a 2 and then 1. Then s term is 0. The constant term is 0, so we write it like this. Okay. So once you have this one, then you put into the numerators and denominator, you hit it, you should get this similar curve like this. Okay. So pretty much, if we continue the different scenario, so if we have a unit parabola, then we simply do it a similar process like this one. Okay. Any questions to the first order system? This should be very easy. And